Well, there are a few possibilities. Todd was
We're
saying
not there yet, though. We have a talk first. That's why this is like...
Oh gosh, I'm really sorry. You didn't even tell me what I'm very pleased to welcome.
Make it short.
Thank you. I'm very glad to be here at this nice workshop, and I'm also glad that Frank Giraldo and Jörn Behrens have already given their talks, so I don't have to explain the numerical methods I'm using. And I can concentrate on this question I'm very much interested in. Are adaptive simulations more accurate than uniform simulations when they share the same amount of CPU time? After a very short motivation, I show you some results that I got in the case of a warm-up bubble test case. I don't want to say with this presentation that everyone should consider warm-up bubbles. It just happened that I was considering a warm-up bubble test case, and I asked this question for this test case. This workshop is just the beginning of this nice program. So the main focus of this talk will be to discuss some open questions that I think should be interesting for this program. I don't think that the discussion in this talk does depend in any way on the numerical methods that are used. However, I want to thank the people that were involved in developing this numerical model. I developed it together with Frank Giraldo, Jörn Behrens, and Volkmar Wirth. We consider the full compressible Euler equations with the discontinuous Galerkin method and a semi-implicit time integration, which was introduced in this way by Rastelli and Giraldo in 2009. Okay, you have already seen such a picture of a space-filling curve that we are using for the H-adaptive mesh refinement of a conforming triangular mesh with the function library which is called Amatos, which was developed by Jörn Behrens. Now I come to the motivation. For this motivation, I show you an adaptive simulation of a warm-up bubble test case. The color shows the deviation of the potential temperature from the background state, and the black lines show the adaptively refined triangular mesh. Inside the warm-up bubble here, the resolution is everywhere about 3 meters, and the domain has a size of 1,000 times 1,000 meters. So I start the movie, and you can see the bubble rises, and the fine mesh is always adapted to the current position of the warm-up bubble. Finally, it reaches the upper boundary, and some small-scale vortices occur. If we wanted to compute the same result without using adaptive mesh refinement, we would have to use this resolution of 3 meters everywhere. As an illustration, I show you here the uniform mesh of the initial condition, the left half, and the adaptive initial condition, what I just showed you. When considering these two simulations, the question comes to my mind, do these two simulations produce the same accuracy? Probably not exactly, because here in the environment of the bubble, we use a fairly coarse mesh. But we could extend this refinement region. So the question arises, where can the spatial resolution be coarsened without losing accuracy? That's the first question that I will consider. The second question is, in practice, we don't have to produce the same results with adaptive simulations. In practice, it is useful to ask, where can the spatial resolution be coarsened without losing accuracy significantly? However, these two questions assume that the finest resolution is somehow given. But in atmospheric applications, we will never resolve all the small-scale processes that we are interested in. So in atmospheric applications, the third question is very important. Given a certain amount of CPU time, is an adaptive simulation more accurate than a uniform simulation? These are the three questions. I think they are important because I would like to know what we could tell meteorologists when they should use adaptive methods and how they should use them. And I show you the results that I found for the warm air bubble test case. For considering the first question, I take my adaptive simulation, subtract the result with the uniform simulation that uses the finest resolution of this adaptive simulation, take the absolute value and get this result here. For making it easier to see, I make it larger. The color map here is logarithmic, so the values here are still in the order of 10 to minus 4 Kelvin. The largest values surround the fine resolution grid. The reason for this behavior is very simple. The warm air bubble is a little bit larger than the finest resolution. And this slightly larger region cannot be represented on the adaptive mesh in the same way as on the uniform mesh. So that is not surprising. Now I take this result and compute the L2 norm and draw it into this plot as a function of the average number of elements until this time I'm currently here considering. It's, in this case here, 200 seconds. In this situation here that I'm showing you, about 900 elements were used on average during the first 200 seconds of the simulation. I did this not only for this fairly small refinement region, I extended this refinement region more and more and got these values here. And here you can see that at this fairly early stage of the simulation, the values where the warm air bubble is not completely covered by the finest resolution show a significantly increased L2 norm. And the other values are almost constant. I think these oscillations here are produced by coarse elements in the edges of the domain. I don't think they are significant. At this fairly early stage, you can still distinguish between simulations that were affected by adaptivity and other simulations that are almost not affected.
If you would take the kind of uniform simulation and then also compute that on the next final mesh and compute this L2 norm difference, so in what range would that error be? Would it be this 10 to the minus 9? So are you kind of hitting the level of kind of discretization error there, or are you already below that?
Can you repeat it? I don't get your question really.
The norm would be 0 because he's comparing with not with the analytic solution, which is not existent, but with the uniform simulation, as far as I understood.
Yeah. So this is comparison adaptive and uniform, but you could also compare uniform with the next final level.
Oh yeah.
And then you would get an idea on how big this, what an L2 norm error of 10 to the minus 9 means in terms of this.
You're right. Yeah, absolutely.
Good point. Good point. I didn't take that. Okay. At this fairly early stage, we can distinguish between these simulations here and these with a fairly low value. But at later times, this becomes much more difficult. And at 600 seconds, you can almost not see which simulations are affected by this adaptivity and which are not. Here on the right-hand side, you can see the situation of the bubble at this time. I think this behavior is reasonable because the warm air bubble produces circulation in the whole domain, which probably has to be covered by the finest resolution almost completely. But I was really surprised that there is not some kind of jump. I would have expected that at some point the L2 norm really jumps to lower values. At later times, there sometimes is some kind of jump, but these jumps vanish fairly soon again. And now the values are just increasing more and more. So I come to the conclusion, adaptive simulations produce never exactly the same result as uniform simulations. That's my result for the first question. It is even more important now to answer the question, when are these differences between adaptive and uniform simulations significant? They should be negligible when the difference is much smaller than the error of the uniform simulation. However, in this test case, we don't know the analytic solution, and I didn't want to spend a lot of CPU time on computing a much higher resolved reference simulation, so I tried to find a different way, and I will explain you now how I try to do it. For this approach, I show you the left half of the warm-up bubble at time 1000 seconds with 3 different resolutions of uniform simulations. Here, 4, 3, and 2 meters. And here you can see the simulations are not completely converged. There are still differences in these perturbations here at the boundary of the bubble. Why do those perturbations, I call them perturbations, why do those perturbations occur? Grabowski and Clark, they investigated those perturbations in a paper from 1993. They couldn't prove this explanation here, but they believe that numerical errors perturb the shape of the initially circular bubble, and these perturbations are then amplified by instabilities. For example, one instability which I think should be important is Kelvin-Helmholtz instability, which I would like to illustrate with this sketch here. If you have a boundary between a wind shear between flows with different densities, then you can show that small perturbations are exponentially growing in time. Grabowski and Clark showed in their paper that there are wind shears at the boundary of the bubble, and obviously there is also there are also different densities. So I think this explanation is reasonable, but I can't prove it. Please let us assume for a few minutes that this explanation is actually the reason for those perturbations. Then we can use those small perturbations as an estimate for the accuracy of the simulation, because if this explanation is correct, then we expect that those perturbations are not there if there is no numerical error. For defining an error estimator, I show you the result for 3 different values of an artificial viscosity parameter. The results I've shown you so far used this viscosity parameter here on the left-hand side, and by increasing this viscosity parameter a little bit, these perturbations vanish. That's reasonable with the explanation that they are produced by numerical errors, because if you increase the viscosity, the correct result gets smoother, and so the numerical error should decrease. And furthermore, the wind shear is decreasing due to the increased viscosity. This motivates the following definition. I consider the minimum height of the 0.15 Kelvin contour at this time 1000 seconds, and I consider it in these red boxes from horizontally from 180 meter to 500 meter, because I don't want to have boundary effects in my domain, and I don't want to consider these fairly strong developed vortices. And vertically, I consider heights up to 600 meters. For the error estimator, I use now the difference between this height in this slightly increased result, slightly increased viscosity result, and the result that I want to test. When I do this, I can compare the accuracy according to this error estimator between adaptive and uniform results with different sizes of the refinement region. And I get this plot here showing the relative error of the relative additional error of the adaptivity in percent as a function of the number of elements of the adaptive simulation divided by the number of elements of the uniform simulation in percent for 3 different resolutions for 3 and 2 meters. And here you can see, as an example, I pick the 3-meter result. According to this plot here, the additional error by using adaptive mesh refinement is smaller than 1% if more than 50% the number of elements of the uniform 3-meter simulation are used. Here I show you the corresponding result. On the left-hand side, the adaptive simulation, and on the right-hand side, the corresponding uniform simulation. According to this error estimator, the adaptive simulation should have an additional error by adaptivity that is smaller than 1% than the numerical error of the uniform simulation. So, as a result, I write the additional error by adaptivity is smaller than 1% of the total numerical error if more than about 50% of the number of elements of the uniform simulation are used. That's my answer for the second question. The third question, now I have to consider, I have to fix the amount of CPU time. And for this purpose, I show you this error estimator D as a function of the average number of elements in total 128 simulations with 3 different resolutions and different sizes of the refinement region. For making it easier to see, I mark the uniform simulation with a red circle and the adaptive simulation that uses the same average number of elements with a black circle. And according to this error estimator, you can see the error estimator is in fact smaller for the adaptive simulation. Depending on the overhead of the simulation, of the adaptive simulation, we have to reduce the number of elements used in the adaptive simulation for really getting the same CPU time. The adaptive simulation is more accurate if more than about 40% the number of elements of the high resolution uniform simulation are used in this case. So that's my result for the third question. I told you, please let us assume that this error estimator is really working, but I'm not 100% sure. So the first open question on my list here is I would like to find better approaches for estimating the numerical error. One possibility is, I think, should be to use a high-resolution reference, like, for example, in this paper by Straka et al. From 1993. In this simulation, they considered a density current that is shown here. I used for this feature here a resolution of 200 meters and a polynomial degree of 3. Straka et al., they compared different 200-meter resolution simulations with a 25-meter reference simulation. And they considered, for example, the amplitude of the density current and the horizontal position of the front. However, I think that this resolution of 200 meters is not suitable for testing adaptivity because you can hardly see really a difference here between the resolution inside of this density current and outside, because the resolution is already so coarse. So I think for testing adaptive mesh refinement, a significantly increased resolution is needed. And that's, in my opinion, also a disadvantage of this approach, because if we want to test whether our results are depending on numerical resolution, we have to increase the resolution again significantly. And I think if the reference simulation needs something like 0.1 meter for our comparison, then I think it's already a lot of CPU time that is needed. So I'm not sure. Well, we should probably try, but I think it's not perfect.
I'm curious, how did you compare two different grids, like the 200 meter with the 25 meter?
In this comparison here, these quantities are compared.
Is it a point-to-point comparison?
In this comparison here, quantities like, for example, amplitude are compared. Total quantities like, for example, amplitude are compared. Okay, an alternative to this approach could be to use a grid conversion study, like it is, for example, explained in a nice paper by Roach from 1997. In this approach, you increase the resolution of your adaptive simulation uniformly, and then you can use some kind of Richardson extrapolation as a reference. The second open question that I would like to discuss is how can we avoid the constant artificial viscosity. I used a constant artificial viscosity, and also Strack et al. Use a constant viscosity. The difficulty is when we just decrease this viscosity, we get more and more small-scale features of the flow. So these results are not really converging at the resolution that we want to consider. This leads me to another question. Which quantities should we consider for testing adaptive mesh refinement? These results will probably still, or should still, converge when considering total energy, for example. But I'm not completely convinced whether total quantities are really those quantities that contain the information that we want to test for adaptive simulations. I don't know. I would like to know. Okay. Another couple of questions is which test cases are suitable or even most suitable for testing adaptive mesh refinement? And does the advantage of adaptive mesh refinement depend on the application? And does it depend on the domain size? For example, I would like to see a comparison of the efficiency of adaptive mesh refinement between a hurricane simulation and a warmer bubble simulation. I would like to know which one is better suited for adaptive mesh refinement. And also, I would like to know how it depends on domain size, because I'm not completely convinced that by increasing the domain size, the adaptive simulation gets more efficient, because maybe just the environmental circulation gets larger, and we have still to cover this environmental circulation. So I think we should consider different domain sizes. The last open question that I would like to mention is probably the most important for meteorologists. How can we estimate the numerical error in more realistic applications? When including moisture or other parameterizations into the simulations, we get significant new sources of errors. And I think this is really a difficulty, because we don't know how they interact with the error introduced by our adaptivity. It may well be that that the result with parameterizations and with adaptivity might seem to get better, but it might be that the adaptivity is just filtering some some weak spots of the parameterization, and so it might be that not really the adaptive method is increasing the accuracy. As an illustration that moisture is making all this more difficult, I would like to show you a moist air bubble. It is from a paper of Stiller and Craig from 2001, and it is implemented into our numerical model by Gabriel Wolf in Mainz. Here, both sides of this picture show the same simulation. On the left-hand side, the moist static energy excess is shown, which is used by Stiller and Craig as a measure of buoyancy of the bubble. And on the right-hand side, I show you the relative humidity. That's from blue to white, and liquid water content, that's green color. The special feature of this setup is that the background of this bubble is almost saturated, and it is moist adiabatic. This has this nice consequence. The bubble rises, the environmental air has to flow downward, and its temperature increases dry adiabatically, making it warmer, and so it has to be mixed into the bubble at a much higher level. So this result is significantly different from the warm air bubble that I've shown you before. And also, this mixing stops the upward motion of the bubble.
Quick question. Do you enforce the symmetry about the x equal 20 line, or does that naturally come out of the grid generator?
That comes naturally out of the grid generator. Okay. As a summary, I show you again the open questions, and I hope that we can discuss some of them not only today, but also during the next 4 months. Thank you for your attention.
So I arrived slightly late, so I apologise. But what is your criteria for actually refining your mesh?
In this warmer bubble test cases, it is very simple. I'm just using the finest given resolution wherever the deviation of the potential temperature from the background state is larger than, I think, 0.1 times the maximum.
So what bothers me is that you've done all this calculation on that just one measure, whereas if you used another measure, you might have had dramatically different results. So did you do comparisons on that?
So far not. I would like to do that.
Because I mean, that's really the whole problem with these sort of comparisons is looking at what the measure is.
Yeah.
Especially, I mean, this is that's a problem that's got a really, really, really easy measure, right? That measure would not work in any realistic simulation. Right?
No, but first of all, I would like to know how to behave if we had a nice measure.
Something to think about for the next 4 months.
If we fix that in the next 4 months, we've really won.
So with respect to the second question of the artificial viscosity, do you need the artificial viscosity as a numerical closure, or are you using that as a parameterization of a cascade of effects from basically the unresolved scales? And relatedly, have you considered any of the Smagorinsky-like ideas that are sometimes used in large eddy simulations?
I have not considered those large eddy subgrid scale parameterizations, but in this framework, I'm more thinking of it as some kind of artificial test case with the viscosity given as a part of the test case. So in this framework, I'm really thinking of it to be part of the test case, and I just want to find out how adaptive mesh refinement can handle this modified test case. But however, I would like to get rid of the artificial viscosity, and I'm not sure if Smagorinsky, for example, how Smagorinsky can work together with the adaptive mesh refinement.
Well, it would change the test case, presumably, in order to. If you want the diffusion, the viscosity to have less effect, you need to choose a more linear test case, fewer nonlinearities. So
Well, I think there's a good reason for using constant viscosity because that allows you to converge the problem.
Yeah.
Because now you have a fixed Reynolds number, high enough resolution will converge it. And so for these kinds of tests where you're varying, resolution and so on, I think that's very handy. Otherwise, the physical solution itself is changing with resolution, and so it's harder to know. It's sort of like that last example you showed that is getting difficult. One of the things we worry about in thinking about adaptive mesh refinement and so on, and particularly in NWP type applications, is it often may not be just a matter of following features that are moving to smaller and smaller scale. With convection initiation, often you have the convection initiating on scales that you can't resolve in the model. And so if you can't see there's anything there, you don't know to put resolution in to let it happen. And so that's one of the real sticklers that we keep churning over.
Good point.
Any more? Let's thank Andreas once again.